Why does one of the twins age slower than the other when traveling at almost the speed of light? How does information live inside a black hole if even light can't get out? Do we have the right to assume that everything that surrounds us may turn out to be a virtual simulation created by mysterious beings? We will discuss these and many other issues in this issue. Each paradox is not just a scientific invention, it is a challenge that forces us to rethink the very basis of reality. From the nature of cause and effect relationships to the structure of space and time at the deepest levels. Our goal is to shed light on these mysteries without removing from the agenda all their philosophical and scientific depth. Welcome to an extended and detailed journey through the most amazing mysteries of space. Buckle up, because some of the clues may well turn your view of the world upside down. Welcome to an exciting excursion deep into the most amazing and brain-blowing paradoxes of spacetime. Here we will clearly see how unstable our ideas about reality sometimes turn out to be. Get ready to reflect on what seemed unshakable and perhaps reconsider your own view of the universe. In total, we are waiting for 25 paradoxes. Grandfather's paradox or grand phasor paradox. We start with the classics, which have become the foundation of many science fiction stories. Imagine that you create a time machine, go back to the past, and prevent your grandparents from getting to know each other. Logically, in this case, your pedigree is interrupted, you cannot be born, and since you are not there, it is impossible to make a journey to prevent something. The main question here is whether it is possible to kill the causal chain if your own role is its direct consequence. Some physicists believe that the universe is self-correcting. Any of your interference in the past will only lead to events that do not change the critical outcome. Others adhere to the idea of parallel branches of reality, where every attempt to change history simply generates an alternative timeline. In popular culture, this paradox has been explored in the films Back to the Future and The Terminator. But at the scientific level, it continues to excite minds and causes heated discussions from the analysis of causality to hypothetical quantum models of multi-world interpretation. The loop startup paradox or bootstrap paradox. The second paradox shifts to a more intricate form of time manipulation. Imagine that you travel through time and give William Shakespeare his own collection of plays. He publishes them under his own name, they become classics, and after hundreds of years, you bring the same plays back to the past to pass them on to Shakespeare. There is an incredible question: where did these plays originally come from? Here we are faced with a cycle without a root cause, since plays arise out of nothing. This contradicts the usual perception of cause and effect, challenging the very essence of the beginning of events. The term bootstrap, pulling oneself out of the swamp by the shoelaces, in this case, perfectly illustrates the idea that an object or information appears without a clear source, forming a closed loop in time. Such ideas have often been played out in science fiction, including in the film Prednist, where the characters are involved in events that close their lives in a self-fulfilling cycle. The paradox of twins. This paradox takes us into the field of Albert Einstein's special theory of relativity. Imagine that you have two identical twins. One stays on Earth, the other goes into space on a ship capable of flying at almost the speed of light. While the astronaut is flying back and forth, years pass on Earth. Returning, the cosmic twin turns out to be noticeably younger than the one remaining on Earth. At first glance, it looks like a logical inconsistency. How so? After all, from the point of view of the twin flying in the rocket, we can assume that this Earth is moving. But the fact is that the brothers are in unequal conditions. One experiences acceleration, turns around, slows down. As a result, taking into account the general theory of relativity, we get different timelines. This is experimentally confirmed at the level of GPS satellites and astronauts on the islands, although to a much lesser extent. The Gemini paradox undermines the intuitive notion that time flows the same for everyone. In the relativistic world, it is relative and depends on the speed of motion and gravitational fields. The farm or farm paradox is a paradox. We move from the rigor of relativity theory to the scale of the cosmos and try to answer the famous question of Enrico Fermi. Where is everyone? If there are hundreds of billions of stars in our galaxy alone, if there are also enough planets around many of them, then why haven't we found any obvious signs of intelligent life outside the Earth? One explanation is the concept of the Great Filter. Perhaps there is a stage or several in the development of life which is extremely difficult to pass. Maybe the birth of life is a rare miracle. Or, on the contrary, intelligent civilizations, having reached a certain level, inevitably self-destruct or move to a level of existence at which we simply do not notice their signals. There are also more exotic ideas, like the zoo hypothesis, when overdeveloped civilizations deliberately isolate us. Or we're just such a young civilization that we haven't grown up to be discovered yet. Fermi's paradox continues to provoke astronomers, biologists, philosophers, and everyone who is trying to understand our place in the universe. The information paradox of black holes, or the black hole information paradox. In quantum mechanics, there is a principle that information cannot disappear without a trace. But what happens when an object with a unique structure, such as a book or even a star, is absorbed by a black hole? Where no light or signal leaves. At first glance, information disappears from the space available to us, but according to the laws of quantum physics, this is impossible. Stephen Hawking discovered that black holes still emit, in the form of so-called Hawking radiation. Gradually, the whole may evaporate, but the question remains where and how the information about the absorbed objects is sewn up. One of the ideas says that it can be encoded at the boundary of the event horizon, as if smearing on a two-dimensional surface. This hypothesis is closely related to the holographic principle, which we will talk about later, until there is a final consensus. Some scientists believe that information is returned in the form of quantum correlations, while others point to potential paradoxical scenarios, like a firewall, a wall of fire on the horizon of a black hole. Schrödinger's cat, or Schrödinger cat, Schrödinger's experimental thinking code, is one of the most famous symbols of the strangeness of the quantum world. Physicist Erwin Schrödinger proposed to imagine a cat in a closed box with a mechanism that is equally likely to either kill the cat or leave it alive during the decay of a radioactive atom. Until the box is opened, the cat is in a superposition, both alive and dead. This paradox raises the question of whether quantum theory, with its idea of superposition, is applicable to macrosystems. We, observing, seem to choose one of the states. Some interpretations, such as the Copenhagen one, say that the wave function collapses when observed, while other multiverse interpretations state that both realities exist in parallel, we just register only one. Schrödinger's code demonstrates how counterintuitive laws are at the quantum level, creating potential conflicts between our large real world and the microcosm of elementary particles. The paradox of Einstein, Podolsky, Rosen, and the paradox. In 1935, Einstein, Podolsky, and Rosen put forward an argument in favor of the fact that quantum mechanics should be incomplete, since it allowed instantaneous communication between particles located at large distances. This effect is called quantum entanglement or inglement. If particles are born as entangled, then knowing the state of one, we instantly know the state of the other, which looks like a violation of the idea that nothing can be transmitted faster than the speed of light. Einstein called it a creepy action at a distance, believing that there must be some local variable hiding from us, but determining the result of the measurement. Experiments, starting with the works of John Bell in the 1960s and ending with cutting-edge experiments with photons, confirm the reality of quantum non-locality. No one has found local hidden variables that could explain it in a classical way. And the paradox points to a fundamental shift in the idea of what is reality, and how objects are interconnected on a quantum scale. The Olbers paradox, or the Olbers paradox. Why is the night sky black, even though the universe contains a colossal number of stars that should illuminate everything around? On the surface, logic says that if the universe were infinitely old and infinitely large, then the rays of light from the stars would fill the entire celestial canvas with continuous brightness. but we see a black void between the stars. The solution concerns the expansion of the universe and the associated redshift of radiation, the final age of the cosmos. Some of the light has not yet reached us, as well as the dynamic evolution of stars and galaxies. Olber's paradox, thus, reveals important aspects of the structure and history of the universe. It was not static and infinitely old. The Boltzmann brain paradox, or Boltzmann brain. Ludwig Boltzmann, talking about the increase of entropy and the possible infinite existence of the universe, asked himself the question: can a random quantum fluctuation generate a brain with all memories and consciousness, but without a real past? After all, with sufficiently large scales of time and space, unlikely events, such as the formation of complex structures, can happen sometime. If the probability of the appearance of a Boltzmann brain for eternity is not equal to zero, then an unpleasant thought arises. Or maybe each of us is just such a random fluctuation, representing the illusion of continuous reality. This hypothesis seems absurd, but it forces us to reconsider the idea of how much we can trust our observations and memories. The paradox of simulation, or simulation paradox. In recent decades, the idea that we can live inside a high-tech simulation created by an advanced civilization has become increasingly popular. Philosopher Nick Bostrom put forward the famous argument that either civilizations do not live up to the level that allows running numerous simulations. Either they don't want to do it, or we are almost certainly already in one of these simulations. Technological trends, such as the development of virtual reality and artificial intelligence, show that creating a world in which the inhabitants are not aware of its artificial nature theoretically does not look impossible. Hence the paradox. If we are a simulation, do we have genuine free will? And what does reality mean? Arrow of time or air of time? A well-known paradox is that fundamental physical equations are symmetric in time, but at the macro level, time moves from the past to the future. We do not see how the fragments of a broken glass are collected back into a single whole. This asymmetry arises from the second law of thermodynamics: entropy increases in isolated systems. Why did the universe initially have such a low level of entropy, allowing this discrepancy in time to exist? There are many hypotheses, from cosmological scenarios to ideas about a multi-world description. But the problem remains extremely difficult, connected with the arrow of perception of time, the psychological arrow, and the thermodynamic arrow, quantum Zeno or quantum Zeno effect. In the quantum world, there is a phenomenon when continuous observation of a particle or system literally freezes its evolution. If a system is in a superposition of states, and we often and continuously measure it, then it does not have time to move to another state. It's like an enhanced fixation of reality due to observation. The paradox is named after the ancient Greek philosopher Zeno, who disputed the continuity of motion. However, in a quantum context, it does work. This effect was tested experimentally. The system becomes less prone to transitions with frequent measurements. The Unruh effect or Unruh effect. According to quantum field theory, even empty space is not completely empty. It is riddled with vacuum fluctuations. For an observer moving evenly, they are invisible. But an accelerating observer can detect thermal radiation right in a vacuum. It's as if space is filled with particles with a certain temperature. It looks extremely strange. What for one is emptiness, for the other turns out to be bathing in a stream of quantum particles. This opens up a fundamental question. What is the true vacuum? Everything turns out to depend on the frame of reference, thereby deepening the paradoxical structure of reality. The Banach-Tarski paradox, or the Banach-Tarski paradox, is already a field of mathematics, but it sheds light on the singularity of infinite sets and geometry. The Banach-Tarski paradox states that it is possible to take a three-dimensional sphere, divide it into a finite but very tricky number of parts, and, by making a series of rotations and permutations, get to spheres, each of which is the same size as the original one. In the real world, such manipulation is impossible because it relies on the use of immeasurable sets of figures that do not have the usual volume. Nevertheless, the paradox shows how much space can behave counterintuitively in higher mathematics, reminding us that our obvious representations may not work in extreme or abstract conditions. The paradox of dark matter, or dark matter paradox. Astronomers have discovered that galaxies rotate so fast that gravity from visible matter is not enough to hold them. The conclusion is that there must be some invisible substance called dark matter. Its gravity explains the movement of stars and galactic clusters, but it does not interact with electromagnetic radiation, remaining invisible. Years of experiments in underground laboratories and space exploration have not yet given 100% evidence about the nature of these particles, such as WIMPs or axions. The paradox is that, although dark matter makes up most of the matter in the world, we know practically nothing about it, and cannot fix it directly. The dark energy paradox, or dark energy paradox observations of distant supernovae in the late 90s, revealed that the expansion of the universe is not slowing down as expected, but rather accelerating. To explain this, the concept of dark energy was introduced, a special kind of energy that permeates space and acts as anti-gravity. The problem is that its nature remains a huge mystery. One hypothesis is Einstein's cosmological constant. The other is a dynamic field evolving over time. Too little or too much density of dark energy in the early universe would not have given it the opportunity to look the way it looks now. Why is she so finely tuned? The paradox of the multiverse, or the multiverse paradox, the totality of many theories, inflationary cosmology, string theory with dozens of landscape forms, a multi-world interpretation of quantum mechanics, leads to the idea that our observable cosmos is just one of countless bubbles or branches. If this is true, then many seemingly random properties of the universe could be explained by the anthropic principle. We exist exactly where conditions are favorable for the appearance of life. But the paradox here is that we cannot directly test other universes. They lie beyond the cosmological horizon or are separated by a quantum barrier. Scientifically, this is controversial. Is the multiverse a real object, or a convenient hypothesis justifying our luck to be in a customizable space? The dilemma of a time traveler, or time traveler's dilemma. In addition to the grandfather's paradox, there are other moral and philosophical aspects of time travel. Suppose you don't kill your ancestor, but you change some historical moment. Could this lead to disastrous consequences for the future? Or vice versa, you will fix some global injustice, but risk improving reality, not knowing that a chain of small effects will lead to more terrible events. Thus, the time traveler faces a heavy burden of responsibility for any interference. It turns out that logical questions here are intertwined with ethical and philosophical ones. The quantum suicide, or quantum suicide paradox, is associated with the multiverse interpretation of quantum mechanics. Thought experiment: a person presses the trigger, which with a 50% probability kills him according to the results of a quantum event, or leaves him alive. With a multi-world interpretation, he dies in some branches, lives in others. But from the point of view of the person himself, he will feel only the branch in which he remained alive. It is believed that subjectively he cannot observe his deadly future, because consciousness is in the branches where the organism has survived. This gives rise to the idea of quantum immortality, which sounds extremely fantastic, but shows how radical the consequences of some interpretations of quantum mechanics can be. The observer effect, or the observer effect, is a paradox in quantum mechanics. The very act of measurement leads to the collapse of the wave function. A particle flying through two slits behaves like a wave until you try to find out which slit it passed through. As soon as you put the measuring device, the wave behavior is replaced by a purely corpuscular one. The question arises, does the observer create reality? Some interpretations believe that it's all about the interaction of the measuring device with the system. Human awareness is not directly involved. But other philosophical interpretations hint at a deeper role of the observer in the universe. The paradox of heat death. or the hit grandfather paradox. Thermodynamics tells us that in the long term, any closed system tends to maximum entropy. The universe, as a globally closed system, must come to a state where no processes take place, there is no energy to support life. Everything is static and cold. This is called heat death or great cold. If the future inevitably leads to a state of no movement, does it not devalue our present? Some philosophers use this scenario to emphasize the fragility and short duration of our era of stars, galaxies, and living beings. Others believe that there may be alternative cosmological cycles or fluctuation scenarios that can delay or restart the course of the cosmos. The singularity paradox or the singularity paradox. Singularities arise in the equations of general relativity. This is the point of infinite density and curvature at the center of the black hole, as well as the conditional start for the entire universe at the time of the Big Bang. But infinities in physics usually indicate that a theory breaks down and needs to be supplemented. The paradox is that we do not have a single quantum theory of gravity that could describe what is actually happening near or inside the singularity. There are hints that singularities can be replaced by some superdense but finite structures or loops, as in quantum gravity loop, or strings, as in string theory. But a complete solution is still far away. The holographic principle or holographic principle is a paradox. Based on the reasoning about black holes, a holographic principle was put forward. All information about a three-dimensional volume can be encoded on a two-dimensional surface. This means that our world is potentially a kind of hologram, where each point inside can be read from the global boundary to some extent. Applying this idea to the entire universe, scientists suggest that all the information describing our cosmos may be on some kind of film at the boundary, for example, on the event horizon, which limits the entire visible universe. This gives a fundamental challenge to the usual understanding of spacetime and material objects, forcing us to assume that volume is a derived phenomenon. Cosmic censorship or cosmic censorship paradox. According to Roger Penrose's cosmic censorship hypothesis, nature hides singularities behind the event horizon. In order to prevent the existence of naked singularities that would be visible to an outside observer, a naked singularity would potentially lead to unpredictability of physics, violation of the causal structure. The paradox lies in the question of whether, in all collapse scenarios, an event horizon is formed before the singularity is exposed. If suddenly it is possible to circumvent these conditions, it means that regions of space with broken causal relationships are possible. This is a serious problem both for astrophysics and for fundamental laws that need protection from infinities. The information paradox in quantum gravity, or behind the information paradox and quantum gravity. This is a unifying super-paradox since the confrontation is between two powerful theories of quantum mechanics, where information does not disappear, and the general theory of relativity, in the interpretation of which black holes can erase information beyond the event horizon. When Hawking showed that black holes evaporate, a problem arose. With the complete evaporation of the object, where does the information go? If the information disappears, the principle of quantum mechanics is violated. If it persists, the question arises, how? Many attempts to solve this paradox have led to new theories, hypotheses, and formalisms. Among them are the holographic principle, the duality of hell-width, sift, firewall, and other exotic ideas. The resolution of this contradiction is one of the main tasks of physics of the new century, requiring the creation of quantum gravity. That is, a general theory combining quantum mechanics and gravity. We have considered 25 paradoxes, each of which challenges our deep ideas about reality. From puzzles with time and travel to the past, to questions about the nature of information in black holes, from strange quantum effects to grandiose cosmological hypotheses. These paradoxes are not just fascinating stories, but the locomotive of scientific progress. Each of them pushes physicists, mathematicians, and philosophers to revise fundamental laws and propose new, more complete theories. Perhaps it is by solving such paradoxes that humanity will eventually make the main breakthrough to understanding the unified theory of everything. Right now, we are only at the beginning of the road. Science has made incredible leaps, but each answer gives rise to a new question. And each paradox indicates that reality is not as simple and linear as it seems at first glance. Tell me, which paradox struck you the most? The grandfather paradox, which touches on causality. Or perhaps a holographic principle that reverses the idea of the very structure of space. Share your opinion in the comments. If this video made you think, please support us. Like, share this video, subscribe to the channel, and write a comment. It's your connection with us, your participation, that inspires us to create even more content for you. And, of course, we want to know what is interesting to you. Write down what you would like to learn about in the following videos. It can be a theme of consciousness, the soul, the mysteries of the universe, or something completely new. Your ideas will help us go further. Thank you for being with us on this journey. See you in the next video.